I'll start off by introducing myself. So I'll introduce the talk first of all. So this is going to be one of these talks which is kind of frustrating. It's frustrating. It's going to be frustrating for me and for you as well, because talking about performance is always problematic, given the fact that everybody who ever talks about performance says you shouldn't be interested in it, really, nearly as much as you are. I think of talks like this as being like the talks you used to get at school on sex education. So you're interested in knowing about sex, and actually all they want to talk about is why you shouldn't be interested. So I'll tell you lots of mechanics about it and say don't do it. And that's a bit what this talk is like. Also, I'm going to apologise in advance. Giving talks about Java 8 is difficult just now because we're in the middle of the adoption of it, and generally I'm finding that audiences I speak to have a much wider range even than you expect of knowledge and ability in Java 8 because some people have adopted it and actually have got a lot of experience of using it, and quite a lot of people just haven't used it at all. And so talks tend to start very I try to please everybody, which of course means I'm not going to please anybody. I start off with stuff that you're kind of drumming your fingers about, and I finish with stuff that's got everybody scratching their heads. So that's possibly how it might be here. So this is me. I hate writing these bio things, so you can take this to mean I don't have a proper job. To just introduce myself. Well, I can shout more loudly. I'm a member of these community programs that Oracle runs, Java Champions and the Java 1 Rockstar Speakers. And I'm a repeat offender in the department of bookwriting. My complaint against Sun and then Oracle was that they took such a long time between these major releases of Java, which I wrote about, was that it was such a long time, it's 10 years, that I'd actually, by the time Java 8 came out and that somebody suggested I should write a book about it, I'd forgotten quite how awful the experience was of writing a book. 10 years is just, it's like, it was too long to remember. The trauma had wiped it out. So if they're quicker, then I'll manage to not write any more books. But it's quite interesting to have written books on the two major changes that have been to Java in its lifetime. There's a really huge difference in terms of the quality, as I understand it, of the process that produced the Java 8 changes compared to those that produced the Java 5 changes, and there's a huge difference in the quality, therefore, of the product. I also, and that's a change for the better, I should say. I also maintain the Lambda FAQ, which was actually where the book came from, but has now become a bit dusty as a result of the effort that I had to put into the book. Needs some work. Still a useful resource if you're learning about lambdas and streams for the first time, I believe. So the agenda for this talk is I'm going to start off with some background. I'm going to talk about, I'm going to very briefly introduce Java 8 streams. I'm going to talk about parallelism and why we're interested in it, because this is, after all, a talk about parallel streams. And I'm going to issue a sermon about microbenchmarking and all the hazards of that. And then I've got a case study where I look at a particular program it was an example that I developed in writing the book and learnt quite a lot from. And I'll look at what we would learn about going parallel with that, and then I've got some conclusions. So first of all, then, streams. Why are we interested in them? Well, the primary reason that we're interested in them is nothing to do with parallelism. Actually, the primary reason we're interested in them is because they bring a functional style to Java. 2 or 3 years ago, when I started getting involved with this, we were just not using the word functional at all, because that frightens Java programmers. Oh, functional programmers, we know these guys are they're very, they look down on us and they know stuff about monads, which we really don't want to go near. But actually what I found actually in writing the book, by the time I got to the end of it, I said, actually we're really learning a lot from them. It's not that Java's going to become a functional language. That's absolutely not going to happen. It's a blue-collar language. That's That's been the slogan for 20 years, and it's not going to change. But we can learn a lot from them, and actually, and we are doing. So we're getting some big improvements in the way that, in the way particularly that we're going to do bulk processing of collections, which is going to make our code much better. Better in the sense of being more concise, more expressive, more readable, and more maintainable. Not in the sense necessarily of being more efficient, although that may come about. And we're also going to be able, and obviously the second reason, the reason that we're in this room today, is that it also gives the possibility of exploiting hardware parallelism. We know that multicore is a big deal, and they wanted to introduce some way of being able to automatically parallelize your programs in a way that would be, as the slogan says, explicit but unobtrusive, and it is. But whether that's a great thing, then we'll see. So the biggest intention, I mean, the big use case is replacing loops for aggregate operations. So instead of writing something like this. Where we have to just to briefly explain this code, I've got a person type and a list of this person type people, and I want to. What am I doing here? I'm filtering the cities that they live in over a predicate which says that the name of them has to be less than 4. So what I'm going to do is I'm going to iterate over this list of person. For each person, I'm going to get the city they live in, and then I'm going to look at the name of the city, and if its length is less than 4, I'm going to add it to a set. It's a very typical kind of thing that we do in bulk collection processing. But the claim is that's not actually very nice. And it's quite hard to read, and I had to explain it in a lot of detail. And it's and I think it's hard to grasp. Brian Getz, when he was doing this, when he was selling the idea of streams at the start, he used to put up a slide like that, and he would say, "Do you understand this?" And if people didn't answer in like 3 seconds, which of course nobody would, because you've got to read the loop, he'd say, "You failed." And now look at this, and the argument is this is a lot easier to understand. So we're going to take the list of people. List of person, we're going to stream it, and now we're breaking out each of the operations separately. We're going to change with the map operation, maps each person into the city they live in. If you use this method reference to do it, that just means call the get city method for that person, and put the resulting city into the stream, and then filter that stream over this predicate that the name of the city should be less than 4, and then collect the whole lot into a set. And the claim is this code is easier to maintain. Well, it's more concise, it's more expressive, it's easier to maintain, and it is also automatically parallelizable. So what we can do is we can write parallel stream here instead of stream, and it will automatically execute. If you're on multi-core hardware, it will distribute the work of the stream over multiple cores. Well, we'll see exactly how true that is and when it's true. So I put in a slide. Streams are a bit hard to understand if you're only used to if you're only used to pre-Java 8 data structures. So you think in terms of collections, for example, and streams are not like collections. They don't hold. They don't hold values, and they're also. I think they're most like iterators in a way because they're lazy. This is very important. The elements are sent down the stream as they're required by the terminal operation, which is often mutable reduction. But actually, I really should have. This picture here should be: we've got a source, a data source, which is put into which the values from that are put into the stream by the so-called splitterator. Every stream is sourced by a splitterator, which is applied to a source, and the stream is actually the values as they pass down it. So it's not even like an iterator. It's not backed by a particular collection. They pass through a number of one or more intermediate operations, and then they are somehow summarized or collected or something at the end by a terminal operation, and it's the execution of the terminal operation which actually pulls the elements down. Up until that point, you can construct a stream from a splitterator, and you can add intermediate operations to it, and the stream remains exercised. No elements will actually be processed from it until the terminal operation pulls them down. So here's a picture of values passing down this stream. In this case, the x0 was mapped into y0 by the intermediate operation, and then the next one comes, and so on. So what are the practical benefits of streams? Well, functional style will affect nearly all collection processing. Automatic parallelism is useful in certain situations, which we're here to talk about. But of course, everyone's interested in performance, and so we need to look at that. Why is this? What's this big deal about parallelism? Well, many people will have seen this graph already. It's from a very famous talk called "The Free Lunch Is Over" by Herb Sutter. I'll put the reference to it on there, but you should read it, because even though it's 10 years old, it's actually 2005 it was first published in. It's taken a very long time for people to really get the message, and the message is the free lunch was the continual doubling of processor speed every 18 months from the time that Gordon Moore first formulated the so-called Moore's law in 1965, 50 years ago. It's unbelievable progress of a continual technical improvement over such a long time, exponential increase in speed. But it stopped. I mean, actually, Moore's law, of course, didn't say anything about speed. Moore's law talks about the number of transistors on a chip, and that's very different. Well, it wasn't different. I mean, you could have confused them up until about 2000 and up until that point there. About the time, in fact, that Herb Sutter was a long way ahead of the rest of us in noticing what was happening. That there was going to be no increase in speed of cores of processors for the foreseeable future with this technology. And there's all kinds of very strong physical reasons why that's the case. It's not going to happen. So I like to say that that at the birth of the microprocessor, a good fairy and a wicked fairy stood at its shoulder, like in the old stories, or at the baptism, whatever. So the good fairy was Gordon Moore. He said, you're going to have lots and lots and lots of children and lots of transistors. We'll find out who the wicked fairy was later on. So we now see chips like this. This is about 2 years old. This is an Intel Xeon 10-core chip. So you can see here are the cores, 10 cores, and a lot of L1 cache here. L1 cache, and some. The L1 cache is going to be with the cores, and the shared caches here in the middle. There's an enormous amount of the because processors are so fast. Then there's almost no point in a way in making them any faster, because the rest of the system components are struggling so hard to keep up. And we get these massive amounts of cache on the disk, because going back to main memory to do processing is like 2 orders of magnitude slower. So cache is really important, and the result of that is that each processor is working with its own cache, and that raises a huge number of issues about how are we going to handle the local copies of data that the different processors have, each in their own cache. And the hardware manufacturers have put a lot of work into both cache coherence algorithms, which make sure that the caches talk to one another, and also into ensuring that the processors will be kept fed with a kind of pipeline of data that is kept replenished. Because having your processors stand idle is a really bad idea. I mean, that's not what, we don't buy chips with 10 cores on them in order to have 9 of them standing cold. Or at least that's what we think we aren't doing, though in practice we'll find that we quite often are doing. And remember that this may look to you like, well, this is a high-end workstation chip, and it's not going to be, we're not going to be seeing very much of this in our machines. But actually that's not true. The number of cores you're getting is increasing substantially. And there's increasingly a trend, especially in server hardware, to do something which I would not have expected. Headless servers have GPUs, of graphics cards installed in them, because graphics cards have been doing parallel processing for a really long time, and they're massively parallel. So this is where an awful lot of processing is going to be done in the future, and we have to find some way of using these cores. And as we're going to see, it's quite difficult. Well, one idea of doing it is a different way of visualizing stream operations. In the previous visualization, I showed the splitterator in iterator mode. Right? So it was taking the elements from this, I imagine an array here, one at a time. X0 went and then X1 went and so forth. But it's called a split iterator because it can iterate over its source, but it can also split its source as well. So I'm going to talk a bit more about this later on, but roughly speaking, the idea is that we're going to see something rather different. After I made this animation, I thought, this is wrong because it gives you an idea that all those elements are going to be, each element's going to be processed in this sort of nice, uniform, harmonious way at the same time. But actually, of course, since we'll look in more detail about how the data is broken down and used by different threads later on, but for now, just know that this nice parallel ordering in which everything gets done at the same time is absolutely unrealistic. What actually will happen is X0 will be taken, and then that thread might be blocked for some reason, and X3 and X1 and X2 will get ahead of it, and they'll all come through at different times, and eventually they're all collected at the end in some reduction, which I'm not going to talk about. Which I'm not going to talk about today. Well, I'll talk about maybe a bit. Yes, I will talk about collection. It's often collection. Sorry, I was remembering where I was going. So actually, this mutable reduction as a terminal operation is very clever, and it's really a big innovation of the Stream API. So reduction as functional programmers have known it, always worked the way it did because they only had immutable values. And Java is a language which does mutation, and typically what you're going to want to do with the values that come out at the end of a stream is you're going to want to put them into a mutable collection. There's really not much other use case in Java for stream processing. And I mean, arithmetic values, yeah, those can be reduced, like you can add them up, or you can get the average of them, or something like that. There are reductions like that, and there are immutable values, a few of them, like value objects and big decimal and that kind of thing. But mainly, we're going to be putting them into collections, and so managing the multi-thread aspect of parallel streams, putting them into non-thread safe collections, is actually a really significant achievement of the Stream API. You don't need to worry about thread safety even when you go parallel. Okay, so the next question is then, that's all background. The next question is, what are we going to measure? And here I'm going to kind of read a sermon about what we measure and how we measure it. We want to know how code changes affect system performance in the systems that we're using. But actually, that's really difficult to do because what we would like to do, I mean, ideally what you would do in a perfect world, if developers were in charge of everything, you'd be able to say, okay, I'm going to here's the production system. I'm going to measure it, how it's performing on the loads that we're getting, and now I'm going to change some code in it just to see what happens, and I'm going to measure how it performs on the same typical loads. But of course, life's not like that. You can't experiment with production systems in that kind of way, and of course, loads vary from day to day. So this controlled experiment under production conditions isn't really is not at all easy to do. So, in fact, what we often end up doing instead is doing controlled experiments under lab conditions, where at least you aren't going to, no animals will be harmed and no production systems will be harmed in the process of performing the experiment. Unfortunately, the problem with this is it's micro-benchmarking, and the problem with this is something that psychologists call the substitution effect. The idea of the substitution effect is that if you're given a difficult question to answer and you don't know how to answer it, you just answer a much easier question instead. So, I mean, the first time I thought of fitting this idea together with the micro-benchmarking was during the election time, and I thought, well, actually, the question you're asked at the election is what political party will succeed in running the country and the economy in ways that are going to give results that you think would be desirable? Well, that's obviously a really hard question to answer. And a much easier question to answer is, how does this guy look on television? And is he good at eating fast food in public? Or whatever. And these are easy questions, and then that's the basis on which people generally make decisions about things. So micro-benchmarking may actually be an example of this. It often is. What you're doing is you find a question that's easy to answer, and whether the answer is relevant or not isn't really that important. So the big problem with micro-benchmarking, which people are not adequately aware of, and I apologize to those here who are, is that it's really hard to get meaningful results from a dynamic runtime. And from Java in particular, the timing methods in Java are flawed. I won't go into detail about how, but both system current time millis and system nano time will not give you good results in many cases. The just-in-time compiler can kick in at any point in the execution of your code. So you were executing, first of all, you were interpreting bytecode. You measure that for a bit, and then suddenly everything changes in the middle of your experiment. And unless you're very careful, if you just take an average over your run, you'll get a meaningless average, because half of it's performed in one condition, under one set of conditions, half of it's performed under another. Same about garbage collection. If in the middle of your observation, garbage collection kicks in, again, if you're not alert to this, it's going to be really hard to get meaningful results. Even looking at standard deviation, which is obviously really important. Averages are just no good on their own. But even looking at standard deviation may not give you the results, meaningful results, because it may not detect consistent deviations, consistent interference. It'll detect random interference, but it won't detect consistent interference. The runtime optimizes code. After it's been compiled, the runtime continues to profile the compiled code, and in most situations, if it finds that it's heavily used, it will optimize it. Sometimes the optimizations may take quite a long time to kick in and may be quite expensive and aggressive. So, and again, that they will really alter the profile of the performance of your code. And if the conditions change, if a thread accesses a lock that it previously hadn't accessed, or if a new class gets loaded so that a monomorphic specialization doesn't work any longer, then it may back out of those optimizations. So the performance of your code may suddenly drop for no apparent reason. So all of these things make it really confusing. And so the short version, the long version is, if you want reliable micro-benchmarks, it's quite hard work. The shorter version is, you've got to get into this. And one thing that I became convinced of in doing the experiments was that you can't eliminate these effects yourself. The worst optimization of all, it's very strange to say worst optimization, that's kind of crazy, is dead code elimination. Because that's really a pain. You calculate, you want to measure how long it takes to do a certain amount of work, but what are you going to do with the results of that work? So, you're not going to print them out to the console, because then the cost of printing them to the console will completely obliterate the actual the costs that you're really looking for. So what do you do with them? Well, if you don't do anything with them, then the compiler will detect that the code isn't doing anything useful, and it will eliminate it. So getting rid of dead code elimination is a major problem, and the benchmarking libraries have worked out ways of doing it. You might think, well, actually, what I'll do is, here's a typical benchmarking trick, and actually it's how at least JMH works. It's like once, in order to convince the runtime that these results are needed, but not to drown out your results with the cost of storing them somewhere. It just stores every 50th one or every 100th one. It uses a random value to work out which ones to store. But the problem with that is that calculating random values is extremely expensive. So if you're not careful, many benchmarks just measure the performance of Java util random. This is the kind of thing which is really, really tough. So often on blog posts you see people putting in system current time, start time equals system current time millis, do something, then the elapsed time is system current time millis minus the start time. And a lot of the time, these so-called benchmarks are really not worth a lot. So the end of the sermon is, ensure that your results are statistically meaningful and more, and get your benchmarks peer-reviewed. So it's just really not an easy business. Okay, so that's the sermon over. Here's the case study. So the case study I wanted to look at was, I was investigating how you could get in a functional style the various options of grep. I just thought this would be quite interesting, and it turned out it was. The one I found was the most interesting was grep minus b, a little-known option for grep, which says that the offset in bytes of a matched pattern is displayed in front of the matched line. So I actually thought, as Java programmers, a solution immediately jumps into our minds for this. It's obvious, isn't it? You declare an accumulator variable, and you just store the length of each line in bytes into the variable, and so when you get a match, you know what the displacement is. But of course, you can't do that if you're going to go parallel, and you actually can't do that with streams, because the idea of streams is you can never really write code that you should never really, and you almost can never really write code that won't perform well in parallel, even if you're going to perform it sequentially. So I'm looking for a solution that doesn't use an accumulator. So that's the problem. Here's my sample code. It's taken from the Roubaix out of Omar Khayyam, and I'm going to try again the joke that doesn't seem to go down anywhere very well. The moving finger writes, and having writ moves on, nor all thy piety nor wit shall bring it back to cancel half a line, nor all thy tears wash out a word of it. So this was written in the 11th century by a guy who was an absolute polymath. He spent all of his time thinking about mechanics, geography, mineralogy, music, and Islamic theology. And I just think it's amazing that he managed to think about immutability as well. No response. Sorry. I thought it was great. Here I'm running grep minus b against that text, and I've chosen some random pattern, w dot star t, and it matches the second line and the fourth line, and it gives 44 and 122 as the byte displacement of these two lines. So let's imagine, correctly as it turns out, that I've written a program to analyze this using streams. Actually, it doesn't matter how it works. So my first question, and I've got it running, and it produces the results, and I'm now thinking of optimizing it. Well, why shouldn't I? Oh, damn! Right, because we don't have a problem. Okay, that would be a reason for not optimizing it. How would we know if we had a problem with this code?
Run extremely slowly.
Okay, what's extremely slowly mean? Pardon? You need to have a baseline. Well, a baseline, yeah. What do you mean exactly by baseline?
By requirements.
Pardon?
It's defined by requirements.
Requirements. It would be really nice, wouldn't it, to have a target. If you don't have a target, what are you tuning for? Why would you want to improve your code? If you don't have an idea about how fast it should be running, you don't have an idea about you can't compare how fast it actually is running. So the first thing to say is you've got to have a target. Otherwise, this is a problem that programmers have. They want to get everything right. I mean, that's our attitude. So you don't have an idea that you should stop working on your program because it's quite correct, but not completely correct. You can't have a program that's too correct, can you? But what about performance, right? How do you know when to stop? There's no point at which you can say, well, you have to have a point rather at which you can say, this is fast enough. Otherwise, you can always find ways of improving the performance of a program, and you're on an endless track. So you need a performance target. Okay, so. Why else shouldn't we optimize code? Well, I'm actually going through a series of, these aren't random suggestions about why we shouldn't be interested in optimizing it. This is the order in which you should be going through them when you think your program's running too slowly. Like, first of all, check that it actually is running too slowly against a performance target. Secondly, check that you've got a problem that actually you don't have a problem that isn't in your process. So let me see if I can manage to give an example of a problem which isn't in our process and how you would detect it. So that's not the one I want. This is the one I want, not your process. So this is a program which actually does analyze. Which actually does do that. Perform grep minus b. So let's have a look. I'll just to prove it. I'll run this on my little text there, and it gives the right answer. And now I'll run it on a much bigger text. This is a 3 gigabyte file. Let's have a look at what happens on big file. And it's going to be running for a while. Let me have a look at what happens. I mean, suppose that we think it's running too slowly. Let's have a look at the activity monitor on this. You've got similar tools on all systems, and you can see that on the right-hand side there, the amount of red in the in the graph is getting really big. This red represents kernel time. So it's not useful time that your program's doing any processing. It's something is happening that's keeping the operating system extremely busy. Right? So immediately, this is a bad sign. The operating system has to handle various kinds of hardware, I/O, disk, memory, network, and so on, and clearly here it's very busy. It's very busy doing that. If we go back to the program, I can tell you, I can show you the cheat that I put in to make sure that would happen. The file reader here is a file input stream, which is directly connected to the input file, and all I'm doing is calling the read method on that. So it's actually reading the characters one by one off the disk. It's no wonder the disk is pretty busy. So obviously that's an extreme case, but you can't conclude because your program is executing slowly that it's necessarily a problem with your code. Well, in this case, it is a problem with the code, but it's a problem with how the code deals with the operating system. So you've got to look at your program in the context of the system as a whole. So let's suppose that we've got rid of that problem, and instead. We'll see what else might be the matter. Supposing we've eliminated the possibility that there's a problem in our process. What else might be wrong? The problem is in our process, but it might not be in our code. What else could be happening in the JVM to slow things down? Garbage collection. Garbage collection is really is actually the biggest user typically, or it can be the biggest user of certainly the biggest overhead in processor terms of the JVM. So let's have a look at not our code. So if I run this, which is actually the same code, except I've now fixed the problem of the I've now fixed the problem with the file reader, and in not our code, I'm looking at the garbage collection logs, and now let's see what happens when we run this. So this will run for a little while, and then we can have a look at the GC logs. I'll just get that set up. So. I'm opening JMeter, which is a free and not very adequate tool. Well, it's a reasonable tool for analysing garbage collection logs. There are more advanced ones, but they cost money. This one's free, and I think we might be ready to look at the. Here we are. Not your code. I'll check that the process really has finished, and open the garbage collection. Oh, right. It says insane data. Right. By insane data, what it means is that it can't cope with this. There's nothing. Really, what happens is that the format of the GC logs changes over time, and they don't necessarily keep up. So it's just complaining about a particular thing there, which I now got rid of. So I should be able to write that file and try again, and we'll see that in this case, hang on, no, it's not your code. VGC, and we open this, and we'll see that we've got 33% GC overhead, which is absolutely enormous. And if we look at the heap usage after GC, then we see that we've got this absolutely insane pattern with many, many full GCs, far more than we want to have. And 33% is like this huge overhead. Now it's not. It wouldn't show up in the activity monitor graph because it's in user space. So the activity monitor will show all green. Yeah, your JVM's really busy, but it's still doing housekeeping. How did I get that to happen? Well, I did something really stupid. I mean, you would never do anything like this in real life. But what I did was I chose a ridiculous survivor ratio. This is an absurd configuration of the JVM. Essentially, I said no survivor spaces. So what this means is that all all new objects have to be put into old space. So you get a massive number of full collections, and that's just going to kill the performance of the JVM. Okay, that's an extreme example, but of course JVM tuning is really the first thing you should be looking at then, before you look at your, before you start thinking about your code. So let me turn off mirroring displays and play this. Right? So there's another reason why you shouldn't. So GC might well be using all the cycles. else there's a problem. And if you eliminated these things, I'm suggesting you should actually eliminate them in this order. Right? This is the order in which, if you've got a problem, you should look for it. So maybe there's a problem in your code somewhere. So now we can consider optimizing. Let's have a quick look at the code that we're going to be using. So the idea, I said I was going to talk about collectors. So I want first of all to talk about how would you implement the problem grep minus b in a functional style, that is, without using an accumulator. So the way I think about it, and I think this is actually quite useful. The way I think about it is, I'm going to look for essentially. I want to end up with some kind of data structure. Now, that's what the square brackets mean. With the lines in the with the lines of the text, the moving finger writes, and having writ moves on, and all thy piety in which shall bring it back to counsel, and so on. These represent the lines of the input file, and what I want to have here, what I'm aiming for, is is a field in some structure here which is going to have the answer that I need. In other words, the accumulative displacement, 0, 44, 80, and 122. So how am I going to get at that? Well, it seems kind of obvious to me that in order to calculate this, then we must have got here by having the individual length of each line in there in the data structure as well. So I'm going to say I probably have these. It would be easy to construct the data, to initialize the data structure for each one of these lines with just these two fields, with just those two fields in. It's the third one that's going to be hard to calculate. Well, let's imagine let's imagine how we might get to this stage from if we were combining partial results, because that's the way that you have to think about solving these problems. You can't think any longer about accumulators. You've got to think about combining symmetrically partial results. So I could get to that from if I had the answer at this stage. In other words, if I had two halves of the answer, you can see how I would do it. Would be I could say, well, the total length of the first half is 80, and so I could add that to each of these two. To add it to each of those two displacements to give the total displacement, and that's how you could combine them together. So 80 plus 0 is 0, and that's that 0. Sorry, 80 plus 0 is 80 actually. So that's that 80 there, and 80 plus 42 is 122. So how would I get to this level? Well, I'd get to this level by it's obvious, kind of merging two things. So this is how you can actually this is the basis of a solution for how you can do without accumulators for this problem. And how do you get these initial partial things? Well, the answer is you just take the line, calculate its length, and wrap it in the data structure. Okay, so when you're thinking about how you're going to collect the product of parallel streams, you have to think about 3 different functions. Actually, you don't have to think about them because the library classes provide the factory methods in the collectors class, which provide you with almost all the collectors you could ever want. But I want to talk about the performance here, so I'm having to look inside of them. Normally you wouldn't go through this process. It's much easier than this when you're actually programming with collectors. So I've talked about how you get these partial solutions. What you do with them when you want to merge them together. But you need another operation which involves adding an element to them one at a time. So I talked about that was the combiner operation that I showed you on the previous slide. And this one is the accumulator operation. And this also shows the third one that you need, which is a supplier. So a supplier creates an empty container, and the accumulator takes a piece of input and adds it to an existing container. So we've also got an accumulator here, taking a piece of input, wrapping it up, and adding it to the container. All right? So these two diagrams actually summarize the solution. Oh, and here's a graphical representation of how you get the stuff to add together. But we've seen that. Okay, so. Supposing I've got this running and it's not working very well, I imagine that it's not working very well. Well, possibly there isn't anything the matter with it. I think I should probably go and take a look at it now. Should I take a look at it now? Well, actually, this would be a point to do that. Let's have a look. I've lost the context of exactly where I should look at it, but I will do. I'm going to do this in NetBeans, which has got a reasonable kind of profiler. So, but I need to mirror displays. So, what's going on here is the collector and the accumulator and the supplier have been defined as above. I mean, the way I just showed them in the diagram. And here is the code that's actually going to do the work. So it's reading from a file. This is the lines method of buffered reader. We introduced in Java 8 to produce a stream of lines from a buffered file, and I'm using the things I just created: supplier, accumulator, and combiner, the ones I showed you on the previous slide, and I'm collecting them together. So what I'm going to get out of that is the data structure that was at the bottom, right? At the bottom of the first slide, that long data structure. It's a deck actually, containing all these lines with their displacements filled in. And then I'm going to actually do, I remember what I was trying to do with this. I want to do some pattern matching. So I'm taking that structure and I'm streaming it again. This is typical of what you have to do. I'm streaming it again, and then I'm going to collect that in a new array deck. But actually, it's quite hard to understand this the way it stands because there's two different sets of streaming going on. So I'm just going to look at the collector that I talked about a moment ago. I'll just comment this out. And obviously we'll not see the overhead of the pattern matching now, but we will at least see the overhead of that collector that I just showed you. So let's have a look at, I'm just going to profile that and see what happens. But notice we haven't gone parallel yet. I'm still working sequentially, and you'll see why in a moment when the profiling results come through. They're actually pretty typical of the sort of thing you're going to see when you try to run streams. So quite illuminating. And it's going to finish soon. And we'll just talk amongst ourselves. Here we go. So let's have a look at the snapshot of the memory from that. And we see that, of course, it's spending all of its time in main. Let's drill down a bit, and we see it's spending all of its time. Look, it's spending all of its time in the collect method. Right? What does that mean? Answer, it means absolutely nothing, because streams are lazy. Right? So actually, when all stream processing is always called from the terminal operation. You'll always see if you profile stream. If you profile the stream program, you'll always see that the root of all the root of the call tree is always in the collect method. Well, let's go and look a bit further. Okay, so now we see that the big majority, the vast majority of it, is in this code here. So I mean, I'm going to cheat now and tell you something that you would find out pretty quickly if you spent much time around this stuff. This is the Java util splitterator's iterator splitterator. So the iterator splitterator is the default splitterator which is used when you can't actually split data. What kind of data can't you split? Well, there are things that are just really difficult to split. You can split arrays nicely because they're in memory. It's easy to work out how to split them. But how do you split, for example, streaming input from a file? Well, you can't really, not very well. There's some heuristics which do a reasonable sort of job on it. But basically, if we're spending all our time in here, in the iterator splitterator, which is a splitterator that can be automatically derived from an iterator, knows nothing about how to actually split the data structure, and therefore isn't very good at it, then you can be pretty certain that all this has to do with the I/O. We're getting this file from off disk, and that is effectively going to kill this. And there's not even any point in testing this in parallel, because parallel processing, because the disk I/O is just not going to be able to feed the parallel streams fast enough. So maybe we'll just take a quick look at the hotspots. Yeah, and okay, that actually totally backs up what I'm saying. So that solution isn't going to work. The reason it isn't going to work isn't just because there's things wrong with that collector. In fact, the collector is going to be order n, so it's not actually great. But that's not actually the main problem. The main problem is the stream source here. Now you might think that I'm sort of still circling around the issue of the efficiency of parallel streams, but I'm trying to put it in context. you remember I showed you at the start that we've got a stream source, we've got the intermediate operations, and we've got the stream sink, the terminating operation. Well, the source and the sink are going to be, the beginning and end of it are essentially going to be executed serially. And I think I mentioned if I can get to it, the two fairies. I will just skip that. The two fairies that stood at the shoulders of the microchip when it was born. The good fairy was Gordon Moore, who said you're going to have loads and loads and loads and loads of processors. And the wicked fairy was Jean Amdahl, who said, but it won't do you any good at all. Right? Why won't it do you any... Well, it won't do you very much good. Why won't it do you any good? Well, Amdahl's law says, and it's really easy to derive, Amdahl's law says that you're going to be really... the overall throughput of your program is going to be very heavily influenced by the amount of the serial proportion of it. So this is too small for me to read, but the top line is the ideal speed up that you're going to get, and the bottom line there is if you've got I think it says 90% is in parallel. So you need only 10% of serial, and you're going to get absolutely no improvement at all after 20 processors or so. So there's just no point in going massively parallel. And in fact, it's worse than that, because 90% is pretty good for lots of programs. So the amount of time you've got for the the amount of improvement you're going to get is critically dependent on the performance of the intermediate operations, because they're the things that you actually want to be expensive, because they're the things that you can save on if you can parallelize. But if you have expensive split operators or expensive collectors, then that's going to be a killer. So we need to get rid of streaming I/O because it's inherently serial, and parallel streams need splittable sources. They also need better collectors, but I'll talk about that in a moment. So the split operator, when the split operator actually works, this is what it looks like. The split operator has a range of the data that it covers, and it will progressively split it down until it gets it till it gets as many segments as you have threads to usefully use it, and then it will iterate over those segments. So for this problem, I thought about a thing called a line split operator. It's a kind of neat idea, and I'm very proud to say that it's probably going to go into JDK9 if I can get myself organized to do the busy work for it. Can you imagine what I'm going to do with that file in order to be able to split it efficiently? What do you know about the Java I/O or NIO that would help me to do that? I hear a muttering. Well, I absolutely do need random access. I do need random access to it. What would be a really good way of getting a file? Memory map files would be just great. That's an efficient way in which the operating system will take your file and essentially you can treat it as though it's in memory. So a map byte buffer is your answer here. And now splitting it is very straightforward. You take some random midpoint, some midpoint, I guess, and then you just look for the end of the line, and that's your split. Right? And then you can split again. So you're always going to split on a whole number of lines. And now you've got your source in a state that you're going to be able to have it as suitable input for the parallel streams. So finally, we get to the story. Parallelizing grep minus b. I actually in the end got very good results, not out of the collector I showed you. The splitting action of the line split operator is log n, as you could see from there. It's just because it's a binary split of the data. The collector no longer needs to compute the index, because the index now is now created as part of the initial data structure. The results I got were pretty good. So the sequential stream was about twice as fast as the iterative solution. I haven't talked about sequential streams, but that looked quite nice. And the parallel stream was about 2.5 times as fast as the sequential stream. So that indicates that that's because the reason for that is because the pattern matching was quite expensive, and parallelizing that work is where you get the really big gain. That's pretty good. On 4 hardware threads, I get 2.5 times speed up. You might think, well, that's far from ideal, but actually it's not that bad. So the lesson of this is that when you want to go parallel, when the workload of the intermediate operations overwhelms or is really significant. It outweighs the overheads when the cost of the intermediate operations and the saving you can make by parallelizing them outweighs the setup costs of the fork join framework, which does the splitting and the collection, which at the end. This is often quoted as n times q, where n is the size of the data set and q is the processing cost per element. It's actually really quite hard. You often know n, but you often don't know q. I made the overhead of this about less than this 100 microseconds. I think the Oracle team, there was quite a big disparity. The Oracle team actually report more than that, about 200 microseconds, and I made it about half of that. So this is really the biggest single lesson. Well, it's one of the biggest single lessons. So another lesson is that some of the intermediate operations are more friendly to parallel processing than others. So the stateful ones are the ones that are unfriendly. Map and filter and so on can be perfectly parallelized, right? Whereas sorting obviously can't be. Clearly can't be parallelized at all. It's a complete barrier. And it's a surprise sometimes that some of those, like limit and distinct, that you wouldn't necessarily expect to be parallel unfriendly, actually are. And that just requires some experience and maybe some micro-benchmarks. Collectors are expensive, or can be expensive. The most expensive thing about them is often what you're doing is you're collecting into a map. That's really very frequent. It's actually also true, I must say, of the other collections, but maps in particular, resizing them is very expensive. Map merges are very expensive. So one thing that I learned that was really quite a big deal was that you want to pre-size your data structures to the size they're going to be, because the repeated resizing is a significant overhead. And the last lesson is, and this doesn't come out of my talk at all, but it's just something I want to say because it's quite important, is that in the real world, you may not be working in the ideal conditions that I've described, where your little Java application has the entire processor, has the entire machine to itself. So it's the threads that you're going to use that are going to be used for the parallelization are drawn from the common fork join pool, which is a default. You can choose a different pool if you want, but then threads in the two different pools are going to be competing with one another against for the cause. And the underlying assumption behind fork join, and therefore behind parallel streams, is that the threads have exclusive access to the cause. And that may be really unrealistic, because not only may there be other applications within your JVM, but also there may be other processors as well on the machine, other processes that also think they should have access to the cause. So in the real world, I think what's really needed in the end is going to be some kind of system administrator's console for saying which thread pools can have access to which cores. But we're quite a long way from that, unfortunately. Okay, conclusions. I'm glad to say, since I'm out of time, performance mostly doesn't matter. Right? So you probably oughtn't to be thinking about it, but if you must, then as a rule of thumb, sequential streams will normally beat iterative solutions. It's not likely that in many practical situations you're going to find that that's a really big problem. Deciding when to go parallel is you want to apply these kinds of considerations. The data's got to be efficiently splittable. The intermediate operations have got to be sufficiently expensive. I've emphasized that, but they've also not got to be blocked on I/O ever. Again, the model really depends on CPU-intensive operations in the threads in the fork join pool, and there hasn't got to be contention for the processors from other processes or from other Java code. It's quite a narrow use case. You need to look carefully, or maybe adapt your program to work with it. Okay, so for resources, there's a document on the web about parallel guidance written by Doug Lee, who was responsible for a lot of the fork join framework. I talked about the Java benchmarking harness, and you can see a talk by Alexei Shipilev, who was primarily responsible for it, which is only one of many talks of his that are available. I think he's really high value, very good. And here's the the URL for the Java benchmarking harness itself. And of course, a really vital resource which nobody should be without is this excellent book on Lambdas, which actually does have a performance chapter in it, which I try to tackle these issues in. So it does make it a bit different from other books on the market. So apologies for running over and preventing us from having any Q&A. I hope you've enjoyed or learned something, or at least stayed awake in this talk. Thank you very much for coming. Thank you.